Hi students, today we are going to study the very important topics in surveying, that is your tacheometry. According to our knowledge, surveying is divided into the two parts. The first one is the linear surveying and second one is the angular surveying. In linear surveying, you have to calculate the areas or distance between the any 2 points in a smaller area. But this method is possible when the area is smaller and horizontal, and it is difficult to find out the distance or elevation of any hilly area is present. In that condition, you are going to the angular survey, जो कि हमने previous lecture में पढ़े हुए हैं. Then in a tacheometry, we are divided into two methods. First one is the Stadia method and second one is the tangential method. In Stadia method, we are also divided the two types. The first one is the fixed hair method and second one is the movable hair method. Today we are going to study the fixed hair method. In the fixed hair method of tacheometric surveying, the instrument employed for taking observations consists of a telescope fitted with two additional horizontal crosshairs, one above and the other below the center hair. These are placed equidistant from the central hair and called as Stadia hairs. According to previous video, we are studying the various types of diaphragms. There is a two veins are available. One is the horizontal vein and second one is the vertical vein. In horizontal vein, there is a two small hairs are available. One is the upper hair reading and the second is the lower hair reading. When a staff is viewed through the telescope, the Stadia hairs are seen to intersect a certain length of the staff, and this directly with the distance between the instrument and the stations. In that case, we have to find the vertical distances also and as well as the horizontal distances also by using the trigonometrical concept. As the distance between the Stadia hair is fixed, this method is called as a fixed hair method. The Stadia method is based on the principle that the ratio of the perpendicular to the base is constant in similar isosceles cycles. In that case, here the O is the instrument station and on the A, B, C is the staff station. From the transit satellite, you have to measure the upper hair reading and the lower hair reading on each staff station. At A dash is the upper hair reading and A double dash is the lower hair reading. In B star, B dash is the upper hair reading and B double dash is the lower hair reading. And C dash, here the upper hair reading and C double dash is the lower hair reading. The difference between the upper hair reading and the lower hair reading is called as the staff intercept. That is denoted by the S. Therefore, the S1 is the staff intercept at A station. S2 is the staff intercept at the B station, and S3 is the staff intercept at the C station. Therefore, distance from O to A is called as D1. Distance from O to B is called as D2. The distance of O to C is called as D3. Therefore, according to the isosceles triangle ratio, therefore, the OC divided by C dash C double dash equal to OB divided by B dash B double dash equal to OA divided by A dash A double dash. These are all equal to constant. The distance OA equal to D1, OB equal to D2, and OC equal to D3. And here the staff intercept is the S1, S2, and S3. Then the constant is equal to K is equal to F by I. Therefore, the final formula for the Stadia method is D1 upon S1 is equal to D2 upon S2 is equal to D3 upon S3 is equal to F by I, where F by I is called as a multiplying constant and F is equal to focal length of the object and I is the Stadia intercept. In that case, constant is equal to K is the 0.5 times cot of beta by 2. Here the beta is the value of, here the beta is the that angle in between the A dash, O dash, A double dash. This angle is called as a beta. Then the case one, when the horizontal side. In that case, we have to consider this figure in which the O is the optical center of the object of the external focusing telescope. B is the point cut by the three line of sight corresponding the three wires, that is the upper hair reading, middle hair reading, and the bottom hair reading. Then B, C, and A is the top, axial, and bottom hairs of the diaphragm. Then the difference between A to B is called as I, and I is the interval backward of the stadia hair, that is the stadia interval. The difference between the AB is called as the staff intercept, that is the S. Therefore, the F, focal length of the horizontal distance of the staff from the optical center of the object. Here, that much is the F1. From this center to C is called as the F1, and this center to this distance, small c, is called as the F2. Therefore, the F1 is the horizontal distance of the staff from the optical center of the object, and F2 is the horizontal distances of the crosshair from center, that is O. Small d, the distance of the vertical axis of the instrument from O, that much distance. The center to M is the small d, and M to staff reading is the D, that is the horizontal distance, that capital D. Therefore, the D is equal to horizontal distance of the staff from the vertical axis of the instrument, and M, the center of the instrument corresponding to the vertical axis. Therefore, the rays AOA and BOB is passed through the vertical optical center. They are straight so that AOB and the small AOB are similar. Hence, due to the similarity of triangles, the F1 by F2 is equal to the S by I. That is the equation number 1. Again, since the F1 and F2 are conjugated focal distance, we have from the length formula. Therefore, the formula is 1 by F is equal to 1 by F1 plus 1 by F2. This whole equation multiplied by the F1. In that case, we have to find the equation F1 is equal to F plus F1 by F2 multiplied by F. This is the equation number 2. From the equation number 1, we are also known the F1 by F2 is equal to the S by I. This put this equation in equation number 2. According to the derivation and simplification, we find the value of F1 is equal to F plus S by I into F, that is the equation number 3. Therefore, the horizontal distance between the axis of the staff is D is equal to F plus D. If you want to see this figure, here the capital D, here the capital D is the small d plus F1. Therefore, we are knowing the value of F1 from equation number 1. Put this value in the horizontal distance equation. Therefore, the D is equal to in bracket F by I multiplied by S plus F plus D, or is also equal to K into S plus C. This is the final equation for the Stadia method. Above equation is known as the distance equation. In order to get the horizontal distance, therefore, the staff intercept is to be found by subtracting the staff reading corresponding to the top and bottom stadia hairs. Means it is the difference between the top hair reading minus the bottom hair readings. That is called as a staff intercept. The constant. Number 1, the K or F by I is known as the multiplying constant or Stadia interval factor, and F plus D is also known as C, is known as the additive constant of the instrument. Then the measuring the distance using tacheometric procedure. According to this figure, we have to set the instrument at any one station, that is called as the center of the station or starting point of the station. At a certain distance, we are holding the staff vertically at a distance of D and measure the upper hair reading and the lower reading of that staff reading. Due to this upper hair reading and lower hair reading, we have to find the staff intercept, and due to this staff intercept, you can find out the distance. Which distance? Here the horizontal distance of the any particular star from the instrument. Therefore, the procedure is for measurement of the distance using tacheometer, that is number one, let the two stations between which we have to find the distance be A and B. Mount the theodolite on the tripodal station, here the tripod station, then center it over station A and also level it. Then make the line of sight of theodolite horizontal. Then this is called as a line of sight. It is a horizontal line of sight. Place a level staff in the vertical position on the station B. This is the station B. Through the telescope, sight this staff and properly focus the image using the object focusing screw. Also make the stadia clear visible by adjusting the eyepiece. Then note down the reading on level staff corresponding to upper and lower stadia. Find the staff intercept, that is the S, by finding the difference between the upper hair reading and the lower hair reading. Then calculate the distance by using the tacheometric distance equation, that is the D is equal to Ks plus C. Since the constants are known as K is equal to 0 and C is equal to 0 and D is equal to 100S. In that case, we are now using the analytical lens. That's why the value of C is 0. Instead of analytical lens, there is some values. Determination of constant K and C. In this method, the additive constant C is measured from the instrument while the multiplying constant K is computed from field observation. Therefore, there is a two method. The method number one is focus the instrument to a distance object and measure along the telescope the distance between the objective and crosshairs. The focal length formula is 1 by f is equal to 1 by f1 plus 1 by f2. The distance between the instrument axis and the objective is variable in the case of external focusing telescope being greater or short sight and smaller for long sight. It should therefore be measured for average sight. The additive constant is known. To calculate the multiplying constant K, measure a known distance D and take the intercept S on the staff kept at that point, the line of sight being horizontal. Using the equation D is equal to Ks plus C for the average value of staff intercept S2, S3 can be measured corresponding to distance D2, D3. Mean value can be calculated.